Just to remind you that the standard cell potentials are in standard conditions. That means the solutions, if you have Ag plus in a beaker, it has to be 1 molar. If you have a gas, for example, let's see if I can find a gas here. It should be hydrogen gas. It has to be, I can't find it right now. It has to be 1 atm. Okay, that's what the standard part means. Certain conditions, 1 atm, 1 molar. Now, when we did the lab, so this is an example of the lab setup. If this solution right here is exactly 1 molar, and if this solution right here, if this is copper plus 2, 1 molar copper plus 2, and this is zinc, 1 molar zinc plus 2, the potential here is what you would get by using the charts. But if these happen to be 0.5 molar, like what I did was I just put a whole bunch of salt in there, I didn't even measure it, the potential is not going to be what you think it would be. Therefore, you can calculate what the potential is if you're not under standard conditions. And that's what we will be learning today. Okay, so EMF stands for electromotive force. It is the voltage of your electrochemical cell. What happens if you're at non-standard conditions? Okay, so as the redox reaction proceeds, the concentration of the reactants, of course, goes down, and the EMF drops until the cell potential is equal to 0. That means your battery is dead, okay, or it's at equilibrium. A scientist, his name was Walter Nernst, a German chemist, came up with a Nernst equation, and what this equation does is it tells you the E, even though you're not at standard conditions. So in the past, we have been calculating this E cell right here is E naught, E naught, E naught. This is E naught, I didn't write it, and this is also delta G naught. Okay, this is delta G naught, standard conditions, and so on. Okay, so what I'm going to do right now is I'm going to derive for you Nernst equation so you know where it came from. You don't have to know this part of the lesson. The final Nernst equation is way down here. It's this one right here. And this is all you really need to know. But maybe you're just wondering, where did the number 0.0592 come from? Okay, so that's what I'm going to show you. So first, we have two equations here. In appendix, or in your equation sheet, you have delta G negative RT ln K and delta G negative NFE. We have used these formulas before, and you also have, and this is what we're going to derive as well later. This right here is the cell potential if you're not at standard conditions. All you have to do is find the standard cell potential and then put in a little adjustment in there, where the adjustment depends on the Q. The Q is the reaction quotient, which is a ratio of products over reactants, which makes sense here. Okay, so what really happens is that as the reactant goes up, you know that reactant goes to products, right? The more reactants you have, the more favorable it is. It's going to go to the right. Okay, if it goes to the right, this number gets bigger. You have a decimal number here. Natural log of a decimal is a negative number, so negative and a negative becomes positive, so your cell potential gets even bigger. So you can make your cell potential higher by changing concentrations. Okay, that's a little bit too much, but let me show you, let me derive it for you first. First, here's the delta G, the equation. Okay, you also know the delta G with a natural log of K. You have those two. This is the delta G equation for non-standard. So if you have non-standard, you have delta G standard conditions plus RT ln Q. We used this in our last chapter, in chapter 19. Okay, Q is the reaction quotient. You may or you may not be at equilibrium. So using these two equations over here, I'm going to plug in this negative NFE in here. So this is non-standard, negative NFE non-standard. Delta G equals negative NFE standard plus RT ln Q. Okay, now we're going to divide both sides by negative NFE, right? So negative NF, negative NF. So here, negative NF will cancel, you're going to get E. Negative NF will cancel, you'll get E, and you'll get RT ln Q over NF. So we have this equation. Okay, so this is the equation that you see in your formula sheet. The formula sheet is negative RT over NF ln Q. Okay, so what I'm going to do is I'm going to simplify this some more. Okay, I'm gonna, R is a constant, and we're gonna say the temperature is 298, and F is also a constant. And I can also take the log of this, and I'm gonna get this is equal to 2.303 log of Q. So that's another constant. So I'm going to combine all those constants, making this formula just a little bit easier to use, and you can do the equations or the calculations a lot quicker. Okay, so here we go. So this is from the formula sheet. What I'm going to do is change the ln Q into log of Q. To do that, ln of Q is equal to 2.303 log of Q. And we learned that here, where did I put it? Over here. Okay, to make them equal to each other, you have to multiply it by 2.303 to make natural log equal to the log. Okay, so what we're going to do is what I did here. Here's the ln, and here's the log, right? So that changed. That means I have to multiply by 2.303. So now I have another equation here. So this is a constant, that's a constant, that's a constant. If we use 298K, that's also a constant. I'm just going to multiply all those numbers, 1, 2, 3, 4 numbers, and use that, okay? So that is going to become here. So 2.303, there it is. There's R, there's T, 298K, there's Faraday's constant. Okay, when I do all that math, I'm going to get 0.0592 J over C, okay? And you know that J over C is equal to voltage. And if you don't remember that, I have a few ways to remember it. Here's the equation. It's written right here. V equals J over C. And another way to remember it for me is Viva Jesus Christ. Okay, so that's how I remember it also. Another way to remember it is also understanding what it means. Voltage is the energy you get for a certain number of charge. Okay? So then the 0.0592 J over C becomes 0.0592 volts. All right, so now you have your formula. Your formula states that if you wanted the cell potential at non-standard conditions, maybe you didn't want to use 1 molar, okay? All you have to do is take the cell potential at standard conditions, and you get that by using the appendix E right here, okay? And then do a little bit of adjustment, okay? This adjustment depends on 0.0592 volts, which is this constant that we got already. N is the number of electrons transferred, and then log of Q, where Q is the reaction quotient, products over reactants, okay? So let's practice it. So here's the equation that I derived. This is all you need voltage right here, okay? So here you go. And by the way, this is not on the formula sheet. So here's the equation. You have zinc, right? Zinc is becoming zinc plus 2. So I wrote that down here, okay? That means it's giving away 2 electrons. Did zinc get oxidized or reduced? You're right, it got oxidized. That means that's the anode, okay? Now the copper. The copper was plus 2, I wrote it here, and it turned into copper solid. Copper plus 2, copper solid. Okay, so it got reduced. It went from plus 2 to 0 using 2 electrons here. So this is reduction, and that's the cathode. Okay. I then looked up the reduction potentials in the chart, and I did the formula. So the cell potential is 1.10 volts. Okay, pause the video to work that out yourself. Okay, then I'm going to plug in all these values in the formula. So the formula states that the cell potential at non-standard conditions is equal to the cell potential at standard minus 0.0592 volts over the number of electrons transferred and the log of Q. Okay, so plugging it in, I'm going to get my E naught as 1.10 voltage minus 0.0592 voltage divided by N, which is 2 electrons, because 2 electrons got transferred, no units. The log of Q. Q is products over reactants. I'm going to solve for it on the side, if you don't mind here. So Q is equal to products, which is, here's the final equation, zinc plus 2, do not put the solid in, divided by copper plus 2. Okay, then I just plug it in. It would be 0.05 divided by 5. And that is, let me just calculate that. Okay, so I got 0.01. I'm going to plug that in here as Q. There you go. So go ahead and do that math. This is 1.10 minus, if you work this out, it is negative 0.0592. Okay, so your new voltage at non-standard conditions, because you don't have 1 molar, you have 5 molars, you have 0.05 molar, is now 1.16. Okay, now let's go back and think about this number a little bit. Your voltage is supposed to be 1.10. You made it higher. As a chemist, yeah, I want my battery to be more powerful, higher voltage. And as a chemist, what did I have to do? Look at the concentrations. All I had to do is increase the amount of reactants, decrease the amount of products, and the reaction makes the reaction proceed to the right, giving your battery more voltage. Okay, if you did that numerically, this is a decimal. The log of a decimal is a negative number, right here, and negative makes a positive, which increases the voltage. Okay, as a chemist, you should know if you increase the amount of reactants, you can make your battery more powerful. Okay, so 20.11 is an example, another example. Go ahead and pause the video and try this yourself. Okay, so for this example, I wrote ahead the CR207 here, the 14H pluses, all the reds, they're all together. Then I'm going to go ahead and count the electrons, okay? To count the electrons, it looks kind of hard. I have 14 pluses here. I'm going to write this down really quickly. Plus 14 electrons, plus 14 charge. A minus 2 here makes a minus 12 on this side. Over here, I have plus 6. Where would you put the electrons? You're right. I would put it on the side that's more positive. And I would, how many electrons would you put? 6 electrons. So now the charge will be equal, right? Minus 6 over here on the, no, plus 6 on this side and plus 6 on this side makes them equal. So it looks like 6 electrons are being transferred. Let's verify that with the other equation. So the equation has the I minus here, the 3I2 here, and put the electrons on the more positive side, 6 electrons. So this one gives electrons, this one takes. This one gives away electrons, it got oxidized, right? Yes, it got oxidized, therefore it's the anode. This one took electrons in, it got reduced, therefore it is the cathode. Plugging into the formula, it's 1.33 volts minus 0.536. Okay, and that will give me 0.79. Okay, this is my standard cell potential if everything were 1 molar. Okay, now I'm going to go ahead and rewrite all this here just to get the final equation so I can solve for Q, because I will need Q into this formula right there, Q. Okay, so let me pause the video and I'll write that in. Okay, so this is aqueous, so you're going to need the molarity for this one. This is also aqueous, molarity here, molarity here. This is a liquid, so you don't put that to the K equilibrium or Q. This is a solid, you don't need that either. So they should give you all these values. Now, if they're all 1 molar, your potential should be 0.79, but they changed the molarity. Here it says that they made this one 2 molar, which is better, right? Again, the more reactants you have, the better. H plus is 1 molar. Let's see, Cr plus 3.001 E negative 5. And it's really good that they have less products. It'll drive the reaction to go to the right. That's nice. I like that. And then 6I minus. Oh, right here, 1 molar. So they didn't really change that. Okay, so I'm going to go ahead and solve for Q. Q is equal to Cr plus 3 squared over, again, this is liquid and this is a solid. You don't need to write those. And then here, Cr207 minus 2, molarity of that, H plus to the 14th power, that's kind of big, and I minus to the 6th power. Okay, plugging in the numbers, I got 2.0 squared over 1. No, I'm sorry. No, I messed that up. It is 1e negative 5 squared. That's this number right here, Cr plus 3, over 2.0 to the first power, 1.0 to the 14th power right there, and 1.0 to the 6th power equals. Okay, go ahead and calculate that. I got 5.0 e negative 11. That would be my Q, and I can tell it's a decimal, right? Negative 11, which would make it the logarithm of this about negative 11, right? So it'll be a negative number. So let's plug it into the formula, which is E equals E naught minus 0.0592 volts over N log of Q. Plugging in the number 0.79 minus 0.0592 volts over N, which is 6 electrons, log of 5.0 E negative 11. Okay, before you do this math, can you predict, will the E become higher or lower than the standard potential? I think it will be higher because you have so much more reactants here. It's going to drive the reaction to the right. So let's calculate that. It is 0.89 volts. It is definitely higher. Okay, so by changing the molarities, you can change the cell potential.